Welcome, everyone. Well, let's get started. So a clarification, again, for problem 1, a reminder that you shouldn't just cite that polynomials are theta of the leading term unless you prove that. We proved some sort of subsets of that in class, and feel free to use similar logic to anything we did in class. But the goal of that problem is really to sort of go into the meat of it. It shouldn't be terrible. You might want to provide a constant for the omega notation explicitly, just to show that something is omega of something else. If this wasn't clear to you, feel free to take an additional 24 hours before submitting, and you can also edit a submission if you've already made one. Send me a Slack message with any questions about this. Does anyone have any questions now? For problem 3, you don't have to go into details about the theta notation. Just because problem 1 is really about that, you do have to actually show the things explicitly. So if something is theta of something else, then it's big O of it, and it's also big omega of it. Any questions? Oh, also, these are meerkats. They're baby meerkats, kind of mongoose. Any questions about anything else in the course? Yeah, they're so cute. Meerkats are awesome. They're also really colonial and collaborative. 24-hour extension if you didn't understand what was involved in problem 1. You don't have to specifically tell me that is why you're taking a 24-hour extension, but yeah. Okay, let's get going. So a reminder of what is involved in a flow network. So we've seen problems, again, this is just repeating stuff that we did last time. We've seen problems, again, like shortest path and spanning tree, where weights on the edges of a graph are basically representing lengths. You can think of them like lengths. And they can also represent the maximum capacity on edges instead. And so a flow network is where the weights on the edges are capacities. And so we have a directed graph where there are weights on the edges, and the weights are called capacities, and they're denoted C. So C of UV. And we assume that there are no self loops in the graph. If there are self loops, we can just change the graph. But assume that there are no self loops. A flow is a function where if you have an edge, the flow along that edge is less than or equal to the capacity along the edge. And the flow is 0 if there isn't an edge there. In addition, you just have that flow is conserved anywhere except the source S and the sink T. The flow is from S to T. And so S is the only place where sort of the net outflow is non-zero. The net outflow is non-zero. The net outflow from S is positive, and the net outflow the net inflow into T is the same thing. And we proved that last time. We can define the value of a flow as just the difference between the net outflow from S and the net inflow. In this case, there isn't, sorry, the difference between the total outflow from S and the total inflow to S. In this case, there are no edges back to S where we're taking a flow, and so the value of the flow is just the sum of the values coming out of the sum of the flow coming out of S. So this is an example of us representing a flow, where here we're saying we're taking 11 along this edge so F is 11 along this edge out of a possible 16, which is C. So the capacity is 16, the flow is 11. These are not fractions, they're just writing both F and C. And again, we have that flow is conserved at any vertex that isn't S or T. So here, for example, at this vertex, we have 7 coming in, 12 going in, and 4 coming out, and 15 coming out. And so 7 plus 12 equals 19, which is the same as 4 plus 15. But at S, the net outflow is 11 plus 8, which is 19, and the flow into T is 15 plus 4, which is also 19. So the value of the flow is the net outflow from S, which is also the same as the net inflow to T, and anywhere else the net outflow inflow is 0. Are there any questions about the definition of a flow network? There's a question about anti-parallel edges that is literally the next slide. Any more questions? Okay, sorry, it's not actually the next slide. It's in a few slides. Maximum flow. So the problem with maximum flow is given a flow network to find a flow with the maximum value. There might be several of these flows. There might be several possible flows with the same maximum value, and we just want to find one of them. Some applications include routing shipments, for example, as we saw in the initial problem last time. How to route shipments in the optimal way if there is a certain capacity, transporting these things. Calculating the flow of water or electricity, because this is sort of modeling what would naturally happen. Airplane scheduling, if the flow along an edge is like the airplanes going from one place to another place, then you need to make sure that you're not having that a flow is not that at each vertex the net flow is 0, because you can't be sending more airplanes out than you're receiving in. Image segmentation, which is going to have to do with the min-cut interpretation of max flow, which we'll see in a few slides. So image segmentation is max flow because it's min-cut. And many other applications. Okay, so now we get to anti-parallel edges. We're going to assume that flow networks don't have any anti-parallel edges, which means that we never have both UV and VU. So why can we make this assumption? Thoughts on why? Suppose that we did have anti-parallel edges. They wouldn't bring anything to the graph. We could just remove them. We would only end up using one anyway. So there are several ways to think about this. So we would only end up using one anyway. Yes, that is true. We would only end up using flow in one direction because the flow itself could be, you could just consider the net flow. However, it's not possible simply to subtract one from the other. What we can do is we can sort of do a stupid thing, which is we can just transform a graph with anti-parallel edges into one without. So here we have anti-parallel edges, and I'm just going to create a new vertex and say, nope, now no longer any anti-parallel edges. And it only increases the graph, the sides of the graph a bit. So there is the question of whether we can just cancel the anti-parallel capacities. Like, i.e. replace this. Suppose we could just take out these two and say, okay, the net capacity is just 6. And this is not true. The reason is because if we had flow in this direction and flow in this direction, the net flow would be 6 in this direction, and we could do that. But for capacity, we can't do that, because that would mean that we just literally couldn't go in one direction. If we had, there is a difference between 10 and 4 and just 6 in this direction. If we had 6 in this direction, we couldn't go in this direction at all. And maybe the optimal flow would be to go in this direction and not to go in this direction. So you can't cancel anti-parallel edges in the capacity, though you could do it in the flow. You can't cancel anti-parallel edges in the capacity, but instead you can just change the graph in a sort of trivial way to create a new vertex. So it's easy, but it's not actually canceling them. Are there any questions about this? But yes, it is correct that one will only end up using or needing one of these directions for a flow, but you don't know which one it is from the start, so you can't just cancel them. Would existing algorithms fail without this modification? It's a convenience for representing doing all these algorithms. It's not going to mess things up, I think. It just makes it simpler to write things down in the next slides. Okay, unless there are more questions, let's move ahead. Cuts. So suppose we have a flow network with flow f from S to T. Oh, there's a question. I guess canceling also doesn't make sense because you could have anti-parallel edges with equal capacity. In that case, canceling would imply you no longer have any edge, which is incorrect. Exactly. And in general, adding more capacity should never restrict your flow. But if you're canceling out an existing capacity, that would be a problem because you would be basically taking away an edge. So adding more capacity is just a good thing. It gives you more options. So you should never be in a situation where adding capacity gives you fewer options. Yep. Okay, so suppose we have a flow network with flow from S to T. So a cut is a partition of the vertices into S, big S, and big T, which are sets. So a partition means that literally every vertex in the graph is in one or the other. So it's in either S or T. And little s, our source vertex, is in the set S, and little t, our sink vertex, is in the set T. Okay. So if you have a cut, the net flow of the cut is given by the sum across all pairs S and T of the flow from S to T minus the flow from T to S. So in this particular case, you would have the flow be 12 across this edge, -4, since it's going back from T to S, and plus 11. So 12 minus 4 plus 11, that's 8 plus 11, which is 19. 19 was also the value of this flow. It was 11 plus 8 coming out of the source, and 15 plus 4 going into the sink. It turns out that it is true in general, that the net flow across a cut equals the flow value. Let's prove this. And you can sort of intuitively think of this as, makes sense, that the flow is sort of what's coming from S to T, and if you cut the graph in any place, then the flow across the cut should just be the same as the amount which is flowing from S to T. So intuitively it makes sense, but let's actually prove it. How can we formally prove this? Anything we've seen which is similar to what we need to do here? anything we can use to prove this? What are some of the statements that, what are some of the ingredients which we will need to use to prove this? Okay. This is a discussion of conservation of flow through a particular vertex. The suggestion of contradiction. We're not actually going to need contradiction, though it's not a bad idea. It just turns out we won't need that. So remember before we showed that the flow into T is the same as the flow out of S. And so we know that the flow, the value of the flow, is equal to this. We know that the net flow into or out of any vertex that isn't S or T is going to be 0. So we can just add some 0 to what we have here. So this is just, all of this is 0. Each one of these things is 0. Because we're just summing over U in S with the exception of the vertex S itself. Now, what is this? We can just simplify all of this. This is S with the exception of the source vertex S. But this is literally what's in here just for U equal to S. So we can just rewrite this as the sum of overall vertices in S, including the source vertex S. And then this sum, the sum of V, flow UV, flow VU. Okay. Any questions so far? So let's break this up now. We can break up the summation for V. We can say, okay, well, either V is in S, because some of these terms are going to be really easy, right? Like for V in S, all of this is going to be really easy, and we'll see why in a moment. And we can and you know the alternative is U is in S and V is in T. So this is the stuff across the cut. We might also break it up like this because we realize that, oh, well, we wanted the stuff across the cut. And so how can we get the stuff across the cut? Well, we could try getting all of this, but in, I guess the motivation for this is like, okay, we want all of these terms because this is the value of the flow across the cut. And we know we can get all of these terms just by adding these zeros to this value of the flow. But then we also have this sort of superfluous stuff, which is the net flow sort of within S. But the net flow within S, this is just 0, because everything appears as UV and also as VU here. So this is 0 plus the net flow across the cut. And so it's just the net flow across the cut. Other questions? This is one of those proofs where the way you do it is basically by saying, I know roughly what I need to use to get where I want, and just sort of playing around with different ways of mixing those ingredients together until you get something that works. That's often the way it works for something that's really intuitive. You say, what do I know? What are the things that I'm definitely going to use in this proof? And you just sort of throw them together in different ways, feeling your way towards an answer. Okay. So now we know that the flow across like any cut is the same as the value of the flow overall. Makes sense. So now we're going to talk about the capacity of the cut. So the capacity of the cut is based upon the capacities of the edges going across the cut. But it's only going to be the sum of the capacities of everything going one way across the cut, from S to T. So here, the capacity of the cut is 12 plus 14. This 9, which is the capacity of an edge going backwards, doesn't matter. So in the net flow, remember, we had 12 minus 4 plus 11. In the capacity, we just have the edges which are going this way across the cut, 12 and 14. It'll be clear why later on. But it's basically saying, how much could you be doing across this cut? So here's another intuitive statement. The maximum flow from S to T is at most the minimum capacity of any cut, S, T. Why is that the case? And spoiler, we're actually going to prove that these things are equal, but we can prove that later, and it's more difficult. Oh, so what do I mean by any cut? Well, there are many different ways to choose a cut. A cut is just any subdivision into an S and a T, where the source is in S and the sink is in T. So another cut would have been putting V3 in S. And then you could have looked at the capacity of this cut, which is these three edges. And then you would have 15 and 11 as the capacity of this cut. So that instead of 23, the capacity of this cut would be 26. Oh, sorry, instead of 26, the capacity of this cut would be 34. I misread the numbers. Does that make sense? Are there questions about the definitions here? Okay. So there is a suggestion that the net flow is at most the capacity of the cut. Maximum flow is defined by the bottleneck. Yeah, so this is basically how we prove it. So suppose we have a flow from S to T, and suppose that we have a cut. Then we have the value of the flow is equal to the net flow across the cut. We just proved that. And that's defined by the sum of all the flow going one way across the cut minus the sum of all the flow going the other way across the cut. And that is just less than or equal to killing this second term. So it's less than or equal to just the flow going one way across the cut. Now that is less than or equal to the capacity of all those edges, the sum of the capacities of those edges. Because you can have at most as much flow along any edge as the capacity. And that's just the value of the cut, or the capacity of the cut. So we have that for any flow and any cut, the value of the flow is less than or equal to the capacity of the cut. So in particular, the maximum flow is less than or equal to the minimum cut. This is very similar to weak duality. when we were looking at linear programming. So weak duality said that the maximum for the primal was less than or equal to the minimum for the dual. And then strong duality came along and said, oh, actually, they're the same thing. And it turns out that actually these two are also going to be the same thing. Max flow is going to be less than or equal to min cut. And sorry, max flow is going to be equal to min cut. The relationship between LPs and max flow min cut is not a coincidence. Questions? Okay. Is the minimum capacity well defined? Well, there are only a finite number of ways that you could create a cut, because there are only a finite number of choices for S. So yes. Okay. Residual networks. Given a flow network and a flow within the flow network, we can define a residual network, which is basically, we can think of it as like, what happens, how can we represent the extra flow that we could take? So if UV is an edge in G, then we have UV and VU both as edges in the residual network. And they have residual capacities. So now we do have anti-parallel edges, but only in the residual network. So the residual network is going to have anti-parallel capacities. This is sort of anti-parallel edges. This is why we didn't want anti-parallel edges in the original network, because it would just make these definitions super hard. So the residual network has, why are there these residual capacities? So the residual capacity from U to V is the capacity, the original capacity, minus the flow that we took. And the capacity in the opposite direction is the flow that we took. Okay, so why is that the case? Well, let's think about S to V1 here. So S to V1, we took the flow 11, but there was capacity 16. So you could think that if we've already done that, we could either add 5 more flow in this direction, or anywhere up to 5 more flow in this direction, or we could take away anywhere up to 11 flow in this direction, because we already did 11 flow in this direction. There's 5 more that we could take here, and there's 11 that we could take back, going backwards. So it's basically just like saying, what could we do to change our original flow? Likewise here, we did a flow of 1 in this direction. So now we have, and there was capacity of 4. So now we could either take back that one, or any subset of it, or we could take anywhere up to 3 more flow in this direction. That's just what's going on in all of these edges. Now, these highlighted edges, don't worry about it. It'll be clear in the next slide why they're being highlighted. But for the moment, just think about, each of these double edges is just saying, in this direction, what is the remaining flow that we could take? And in this direction is, what is the flow that we could subtract, because we actually were assuming we were already taking that flow in this direction. I have questions about the definition of a residual network. Here, there's an edge only in one direction, and that's because we took the max amount of flow in this direction. So there's no way for us to take any more flow. And you could think of it as being just a 0 edge in this direction. In general, I'm not really going to distinguish between having 0 weight edges or 0 capacity edges and just not having those edges, because a 0 capacity edge is useless. Does it somehow relate to deep ResNets in deep learning? No, but very good question. No, it's just an unfortunate similarity in naming, which I totally didn't realize until now. So thank you for pointing that out. Now I won't be able to unsee it. Yeah, do not call this a ResNet. It's not a ResNet. It's a residual network. Is the residual network a flow network? I mean, sort of, but it doesn't have the property of the original flow network, which we were assuming didn't have anti-parallel edges. We should think of the residual network as basically a flow network, but it's a flow network that we're calling a residual network because we're going to do something different to it than the original flow network. Okay. More questions? Move on. Okay, so what do we do with the residual network? Why do we have these residual networks? So given a flow network and a flow from S to T, an augmenting path is a path from S to T in the residual network with positive capacity along all edges. And this is why residual networks are important. So here, again, this was a flow, and we created a residual network. And now the reason why these are highlighted is because this is an augmenting path. And this is what it is just a path from S to T, and all of the edges have positive capacity. Now, why is that interesting? Well, because we can add to our original flow. We can say, okay, what's the minimum of all of these? The minimum edge capacity along all of these edges is 4. And so we can add 4 to the flow along these edges. We can take this flow, and we can say, okay, we're going to add 4 to the flow here. Now it's 12. We're going to add 4 to the flow along here. Wait, we can't add flow here because this was an edge going in the opposite direction. But what we can do is we can take it away. So now there's 0 flow in this direction. There used to be 4. And so here we now add 4, and we go from 15 to 19. And so this is now a new flow where we've added 4 net flow from S to T. So we've increased the amount of the flow. That's cool. If we're trying to create a max flow, this sounds like a good way to go because we've created a flow which is bigger than with a value that's bigger than the original flow. And this is the new residual graph. Like you can create another residual network. You can create another residual network here, where here, for example, instead of being 5 and 8, because there was 5 that you could take more in this direction, 8 that you could take, the 8 that you could take back. Now, since we're taking 12 flow in this direction, we could take back anywhere up to 12 in this direction, or we could add anywhere up to 1 more in this direction. All right, any questions about this? An augmenting path is just a way to increase the flow along a particular path through the residual network. Okay. So the Ford-Fulkerson method, Ford-Fulkerson, is just basically a method for creating max flow, finding max flow based upon the this idea of residual networks and augmenting paths. In the case of this example, so we found an augmenting path, we added it here, we created a new residual network, and then we could find another augmenting path here, and we could add it again to the flow and keep on doing that. So the method is just start out with a flow which is 0 everywhere. That's sort of how you initialize. Find an augmenting path in the residual network, update the flow by adding flow along that path, and just repeat. Find another augmenting path with a new residual network, update the flow. Find a new augmenting path, update the flow. Keep on doing this. Keep on updating your residual network too, of course. When you finally don't have an augmenting path anymore, then you are done. This is not a proof that this works. What we've seen, what we have convinced ourselves of, I think, is that if there is an augmenting path, then we're able to increase the flow. But we haven't convinced ourselves that, for example, if there isn't an increase in augmenting path, then there isn't a way to increase the flow. This is sort of a greedy approach where you're increasing the flow until you can't go any higher. But maybe there's another way that you could have had a flow which was better than going this way, but you can't get from here to here. Maybe you're like in a local optimum. And we'll prove why that's not the case in a few moments. But first, let's just see again how this works. So here, we can start out with a graph here. A flow network. And here, this is just a flow network with no flow along it. So a flow network with no flow along it is going to just have itself as the residual network, because there are no edges going in the opposite direction. So we find an augmenting path. It's just a path. Here's a path. How much flow can we put along this path, this particular one? Four. We can put 4 along this path. That's just because it's the minimum of all of these capacities. Thinking about it as like, putting water on the pipe, and there is only capacity for putting so much water. And the bottleneck edge is here in this case. Okay, so we have flow of 4. Now this gives us a new residual. Sorry, this gives us this amount of flow. And now we create another residual network. This is the new residual network. And here is an augmenting path like this. This we can also take flow 4 in, because this is the minimum edge here. And so we can augment our original flow by adding 4 along each of these edges. We create a new residual network here, and here is an augmenting path here. And again, seem to be a lot of 4s going on. We can take 4 here. Notice that when we're taking 4 here, this is actually canceling out the flow that we originally took in this direction. That's why we can take this 4 in this direction, and we end up with another flow here. Any questions? We can carry on in this way until we eventually get to this flow. And this flow has this residual network. And there isn't an augmenting path here. And we can sort of convince ourselves pretty easily of that. Suppose we try to create an augmenting path. Okay, we can go from S to either V1 or V2. If we're going from V1, there isn't actually an edge out of V1 except going back to S. So there isn't a good path going through V1. But there is an edge going out of V2. So we could go to V2, we could go to V4. That's our only option apart from V1, which doesn't help us. So V2, we could go to V4, but then V4, there isn't a way to get anywhere else. We cannot ever get out of these 4 vertices. Okay. Questions? Okay. So we're going to prove the Ford-Fulkerson method by showing that the following are all equivalent. That we have a maximum flow, that the residual network contains no augmenting paths, and that the value of the flow equals the value of a cut for some cut in the graph. This is called the max flow min cut theorem, because as a corollary to it, we have that the maximum value of a flow is equal to the value of some cut. And since we know that the value of the flow is always less than or equal to the value of a cut, this means that the min cut is equal to the max flow, because we know that the min cut couldn't be less than the max flow. I mean, I guess that's just saying that there isn't a cut which has smaller value than this. So this has to be the min cut. If there were a cut that was smaller, then we would have value of f be greater than the value of the capacity of that cut. And we know that's not the case. So as a corollary of this, we get max flow is equal to min cut. But in addition, we will get that if we don't have any augmenting paths, the important part for Ford-Fulkerson is if we don't have any augmenting paths, then we know that we have a max flow. But this is going to be useful in proving the theorem. The way in which we're going to prove this theorem is to show that all of these are equivalent. So this, if and only if this, if and only if this. So any 2 of these are in if and only if. Are there any questions about the statement of the theorem? Okay. For the proof, can we show that A is implying B is implying C is implying A? Yes, that is exactly what we will do. And that is often that is why one has theorems with 1, 2, and 3 are all equivalent generally. Or sometimes, 1, 2, 3, 4, 5 are all equivalent. A good way to prove them is to show that one of them implies another, and then it circles around and implies the first. Now, why is this enough? Remember, previously, if we had just 2, it would be 1 implies 2 and 2 implies 1. That's what an if and only if statement is. 1 implies 2 and 2 implies 1. Well, how can we get away with never proving 2 implies 1? Well, we do prove that 2 implies 1. We just prove that 2 implies 3 and 3 implies 1. And so that proves that 1 implies 2 and 2 implies 1. And likewise for any of them, like if you had 3, that implies 1, but then 1 implies 2. And so we know that for any of them, you can sort of circle around and prove any of the other ones is true. Does that make sense? This is a way to show that all 3 of the statements are equivalent by this sort of cycling argument. Okay. So there are 3 things we need to prove. 1 implies 2, 2 implies 3, and 3 implies 1. Why does 1 imply 2? Doesn't have to be a formal proof. Often when we're doing these kinds of proving multiple parts of a theorem, there's one direction which is easy, or a couple of directions which are easy. And so we're just going to sort of pick off the easier things first, and then deal with the harder one. Why does 1 imply 2? Intuitively. Yeah, if there is an augmenting path, then you can add it to the flow. And so we can get a bigger flow. So if 1 is a maximum flow, then we can't have any augmenting paths, because if we did, we could make the flow bigger. It's basically a contradiction argument, yeah. Okay. Why does 3 imply 1? I'm going to come back to 2 implies 3. Why does 3 imply 1? Suppose that we have 3. So the value of the flow equals the capacity of some cut. Could there be a larger flow? Could 1 be false, supposing that 3 is true? Yes. So before we proved that we can't have more flow than the capacity. So if we know that the value of the flow is always less than or equal to the capacity of the cut. So if we have that some flow is equal to the capacity of the cut, then it has to be the maximum, because if we increase the flow, we would be violating that flow is less than or equal to cut. Okay. So now we have the 2 easier directions. 1 implies 2 and 3 implies 1. Let's do 2 implies 3. So 2 implies 3 is, suppose that the residual network contains no augmenting paths. Then we need to prove that the value of the flow equals the capacity of the cut for some particular cut. And again, if we have no augmenting paths, then that means that there is no path from S to T in the residual network having all positive capacity edges. I'm just going to sort of admit the having all positive capacity edges, assuming that a path has, path is a path with all positive capacity edges. So what might be a good cut to consider? Can we describe a cut that we can then try to prove is this nice cut that we like, where the capacity of the cut equals the value of the flow? Can we define such a cut? What is the set S? What is the set T? We can let S be the vertices reachable by S. This is a reasonable thing to consider, because remember, we need S and T to be such that the set T contains T and the set S contains little s. So we know that T isn't reachable from S. So we could imagine that big T is all the things that aren't reachable from S, and S is all the things that are reachable from S. Okay. Yeah. So recall the definition of the residual graph. If UV is an edge in G, then GF, the residual graph, has the residual capacities, this and this. The capacity UV is just whatever was left over. The capacity VU is whatever the flow was. So we could go back with whatever up to the flow that we had. And we could also take any additional flow that was left over from the capacity. Suppose we have an edge across the cut with U in S and V in T. Let's look at the capacity of UV. Well, because T is unreachable, V, because V is in T and T is the unreachable vertices. We know that the capacity has to be 0 because we couldn't get there from U. There isn't a path from S. There is a path from S to U, but there isn't a path from S to V. And so there can't be, there has to be a 0 edge here. But that means that this is equal to 0. So the capacity in the original graph is equal to the flow. And it also means that there isn't any backwards flow, because then if FVU was positive, then you would have this definition giving you some CF. So you can never have any sort of residual capacity, and you can't also have flow in the other direction, because then this would be equal to the flow that you were taking in the other direction. Let me show what this looks like in this picture here. So we had, this was a situation where we couldn't do anything more. These are the vertices which are reachable from S. This is the set S. And this is the set T. These are the ones which aren't reachable. You can see that there are no edges from here to here. That's just by the definition of reachability. But that means that there is no flow, that in each of these cases, the flow from one of these vertices to another one exactly matches the capacity of the edge. So the flow here is 12 out of possible 12. And here the flow is 4 out of a possible 4. So there's no way to use any additional capacity. And also, there isn't any flow from anything over here to anything in here, or else we could just go back. So again, we have these two things that follow from this being 0. That the capacity is equal to the flow in the original graph, and the flow backwards across the cut is 0. Now, the value of the flow we know is equal to the value of the flow, the net flow across the cut. We proved that that was the case. And that's equal to this by definition. Now, let's look at this term. We know that this is equal to the capacity. And we know that this term is equal to 0. No flow backwards across the cut, and the flow forwards across the cut is the max possible. So that's just equal to the capacity of the cut. Whoa, done. That's just the definition of the capacity of the cut. Are there any questions about this? What we did was we suppose that there is no augmenting path. We showed that if you take the set of vertices which are reachable from the source and the set of vertices that aren't reachable from the source, the cut between those two, reachable within the residual graph, the cut between those two in the original flow network is going to have capacity equal to the value of the flow. Let's go back to what we were trying to prove. We were trying to prove that 1, 2, and 3 are all equivalent. We proved 1 implies 2, 2 implies 3 is what we just proved. And again, we previously proved that 3 implies 1. So in particular, that means that the max flow is equal to the min cut, as we previously noted. 3 and 1, if you just take those two, then you get that max flow is equal to min cut. And if you just take 1 and 2, then it shows that when you don't have any augmenting paths, you found the max flow, so the Fuller-Fulkerson method will eventually give us a max flow, assuming that it does converge. Now, I'd like to finish by talking a little bit about running time. We're not really going to get into this, but assuming that all the weights are integers, which is a big assumption, how long might this take? I'll let you think about it for a moment, but then I'll just tell you the answer. So each augmenting path that you add, you can think about how many augmenting paths you're going to add, how many times you're going to iterate, and also how long it takes to do a single one of these iterations. So each one of those augmenting paths is going to increase the flow by at least 1, since each flow value is a positive integer. You started out at 0, you add at least 1 each time you add an augmenting path. So the number of iterations is at most the value of the maximum flow. Now, how long does each iteration take? Not really going to go into this, but it's just trying to find a path in the augmenting network and in the residual network. But you can do it in order of time equal to the order of magnitude is the number of edges. So the total amount of time is just number of edges times the value of the maximum flow. But, and I'm not going to go into that, there is a faster way to do it which doesn't rely upon the value of the maximum flow. The Edmonds-Karp algorithm is just a variation on this approach, which means that you can do it in order of magnitude, in big O of number of vertices times number of edges squared. Are there any questions? That is the end of class for today. We will pick up again on Monday. Again, if you joined late, I encourage you to, I can go back to the first slide where I just mentioned that problem number 1, you should be making sure not to rely upon, you make sure if you're saying that polynomials are theta of their leading term, you should prove that. If you just cite it, then that's not enough, because we didn't really prove that in class. You may, and the goal of the problem is to get you to dive into the definition of theta notation. You may want to provide a constant c for the big omega explicitly, And if this wasn't clear to you, feel free to take an additional 24 hours before submitting or editing your existing submission on my courses. You can Slack message me with any questions. I'll stick around for a couple of minutes for questions. Thank you all for coming. Have a good weekend.